ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be going over the second part of Chapter 5 from Zumdahl Chemistry 7th edition, all about gases. So when we last left off, one of the gas laws that we haven't exactly talked about is Dalton's law of partial pressure. So what does Dalton's law say? Dalton's law says that if you have a mixture of gases in a container, so suppose you have I don't know, some sort of giant tank, and it contains 3, 4, let's say 5 different gases. You've got nitrogen, oxygen, let's say we've got carbon dioxide, helium, argon. If you're looking at the total pressure of that container or that tank of gas, the total pressure is going to be equal to the partial pressures of each of the gases. So in other words, if I knew the pressure of just the nitrogen and the pressure of just the oxygen and the pressure of the carbon dioxide and the pressure of the helium and the pressure of the argon, I could theoretically add those 5 pressures together and find the total pressure of that gigantic tank of gas. So Dalton's law is based on a couple of assumptions, but here is just a visual example of that. So suppose that I know that this can of gas is 0.5 atmospheres, and this is 1.5 atmospheres. So if I didn't change the volume, notice it's the exact same volume as the previous two, but if I were to mix these together in the same container with the same volume, I would just add them together. So the pressure of the total would be P1 plus P2, which would be equal to 2 atmospheres. And that's Dalton's law of partial pressure. So here's an example of how you can use Dalton's law of partial pressure in order to solve a seemingly simple problem. Now this actual problem has 2 methods you could use based on all of the previous gas laws we've talked about in order to solve it. And I'm going to show you both ways because they're both great approaches at figuring out what's going on in this problem. So consider the following apparatus containing helium in both sides. So I have helium here, and I have helium here at 45 degrees Celsius. This is the valve that is closed. So I have helium on this side, helium on that side. What do you think is going to happen when I open the valve and now the 2 sides mix? I'll tell you a common mistake people would make. The first thing is people would say, oh, we just went over Dalton's law of partial pressure. 2 atmospheres plus 3 atmospheres. Okay, 3, 4, 5. That's 5 atmospheres. And I'll tell you why that's wrong. So remember, in fact, you know what? I'm going to go back. Dalton's law of partial pressure is true if, right here, notice the volume is exactly the same. The volume is not the same in this situation. All of a sudden, I go from having, in this case on this side, 9 liters, and this side 3 liters, to having, again, a greater volume as the total. So now, thinking through this, how can I solve this? Well, I'm going to show you 2 methods. Here's the first method. So obviously, we're going to have to use Dalton's law eventually, but if I'm looking at this as a regular problem, I see atmospheres and liters, I see Boyle's law, right? Pressure and volume, that's what I see. So let's find, using Boyle's law, the pressure that would be experienced in this change. So I'm going to mark the left side as red and the right side as blue. Now picture this. I have 2 atmospheres and 9 liters. That's nice and easy to picture here. Now, when this valve opens, the after effect is going to be now I have 9 plus 3. So now notice 9, 10, 11, 12. I have 12 liters worth of volume now. That's going to change the pressure. It was 2, now it's going to be something else. What would that be? Well, when you do your Boyle's law, you get 1.5. And that makes sense, right? Logically, if the pressure is 2, and at 9 liters, now I'm at 12 liters, the pressure should go down because I have more space. That should hopefully make logical sense. I can do the same thing on the right side. 3 atmospheres and 3 liters, great, but now I'm opening the valve up, let's say, and I'm going to have a new volume. I would have 12 now. And what would we expect? Of course, right? Makes sense. Again, the pressure is going to go down from, in this case, 3 atmospheres to 0.75 atmospheres. Why such a big difference? Well, think about this. This was 3 liters, and now it's going to 12, when you look at both put together. So, of course, this is going to have more of a dramatic decrease than this. Now, using Dalton's law of partial pressures, I can add them together and get 2.25 atmospheres, because now, look, the pressure of each one of these here, now the volume is constant, right? It's as if I am looking at 2 gases that are being added together simultaneously in the same container. So that's one way of solving it, using Boyle's law and then Dalton's law. Now, here's another thing that you might notice. You might say, okay, I have this information. I also have the 45 degrees Celsius. That sounds kind of like maybe I could use the ideal gas law. Because remember, for the ideal gas law, you need PV and RT. Well, if I have PV and I have T, that means that I could find the number of moles, right? So how might that help you? Well, I'll explain. But let's again look at the left side as being red and the right side as being blue. Well, let's plug this in. So I have 2 atmospheres, 9 liters, and again, I have N, my number of moles. This is my R. This is my ideal gas constant, or the universal gas constant. And then remember, you always have to convert this, so 45 degrees Celsius, to Kelvin. So that's 318 Kelvin. When you do that, I get 0.689 moles. I can do the same thing on this side. So 3 and 3, blah, blah, blah. Everything is the same, 0.345 moles. Great. What can I do now? Well, now I could basically add these together, because that's what I'm doing. When I open the valve, I'm adding together the contents of this side and the contents of that side. When I do that now, think about it. Again, the volume has now changed, right? I've gone from 9 liters and 3 liters to 12 liters total. So I can now do that. First, again, add together your number of moles. You get 1.034. Total volume, 12. So now let's plug that into PV equals nRT. I have my new volume. I have my number of moles of gas. I have my constant, and I have my temperature. Now, solving for pressure, guess what you get? 2.25 atmospheres, the exact same answer as before. So I love these types of problems where you could technically approach it 2 different ways, and yet everything works out exactly the same. It's always nice to know if there are 2 or more ways of solving a problem, then that just means you have to kind of think through the logic of it in order to solve it. Here's another one, 27.4 liters of oxygen at 25 degrees Celsius and 1.30 atmospheres, and 8.50 liters of helium at 25 degrees Celsius and 2 atmospheres were pumped into a tank with a volume of 5.81 liters at 25 degrees Celsius. Calculate the new partial pressure of oxygen, helium, and then the total pressure of both gases. All right, we can do that. So let's again look at our nice little Boyle's law here. I've got oxygen here, 1.3 atmospheres. I've got 27.4 liters. And now the new tank is going to be 5.81 liters. Notice that the temperature is the same in every single one of these situations, 25.0, 25.0, 25. So that means that the temperature is negligible. I don't have to worry about that. I could literally just use Boyle's law. So I can find P for this situation. And when I do that, I get 6.13 atmospheres. Okay, what about helium? Let's do that. Same exact process, right? 1.3, 20, where is it? 27, yeah, 0.4. And then I've got my new volume for the tank, which is 5.81. And then again, when I look at that, what do I get? I get 2.93 atmospheres. What would be the total pressure of both gases? Well, again, we've got Dalton's law here. We can add them together and get 9.06 atmospheres when we add both of these together. Again, think through this logically. I'm starting with 27.4 liters, and now I'm decreasing it. What should happen to the pressure? Well, it should go up. So 1.3 atmospheres, it goes to 6.13. Here, again, I'm going from, again, 27.4 to 5.81. Notice that all of a sudden I end up with, again, a net increase of the partial pressure. And when I add them together, you can guess that I get to use Dalton's law finally, since that's what this section is all about, and I now get a total pressure of 9.06 atmospheres. All right. So let's talk a little bit about 5.6 here, which is about KMT, that's what I call it, at least, kinetic molecular theory. So here's the thing about kinetic molecular theory. It has four, let's call them suppositions. Okay, so four, postulates, four ideas. The first is particles are tiny. Okay, so the particles of a gas are going to be so small compared to the distance between them that we can assume that the volume of the individual particles is basically zero. Now, kinetic molecular theory is not saying that these are true. Like, obviously, we know that, the volume of an atom is not zero. But, okay, for all practical intents and purposes, the volume inside of an atom compared to the volume of, like, a tank of gas is going to be so ridiculously different, right? The tank of gas is going to be so huge compared to the tininess of the individual atom's volume that we can basically assume that it is, a limit that approaches zero in some way, shape, or form, okay? And so what that means is gases are special. When I'm looking at gases, there's so much distance between the particles that I can pretty much assume the particles are little points, like little dots that are knocking around on the inside of their container. Now, the other little postulate of kinetic molecular theory is particles of gas are going to be in constant motion. What does that mean? The gases are always going to be moving around. They're not going to stay still. That also means, though, that if we're looking at pressure, what's causing pressure, the pressure is caused by all of the collisions between the particles and the container. So every time one of these particles touches or bumps into one of the sides of the container here, that's going to generate some pressure. And that's what we measure when we measure pressure. Now, the particles are also assumed to exert no forces on each other. In other words, they are perfectly, balanced. So in a way, they will always, just like two balls hitting each other, ricochet off. They're not going to absorb each other's energy by impacting. They're not going to attract each other or repel each other. Now, again, we know that that's not necessarily true, right? That there are some forces of attraction that atoms and molecules of gas are going to exert and feel on one each other. But again, we're going to assume that we can basically ignore that effect. And then last but not least, this one's just hard to kind of picture, but the average kinetic energy of a collection of gas particles. So if I were to have a tank of gas, the average kinetic energy is going to be directly proportional to the temperature of the gas in Kelvin. Again, that one's kind of hard to picture. The other ones are a little bit easier. Now, kinetic molecular theory is kind of the basis for how we're able to use all of the gas laws that we've talked about. So the ideal gas law, combined gas law, and Dalton's law all kind of assume these things to be true. And so let's check some of these concepts first of all. So let's say that I have two balloons, okay? They're the same size balloon, by the way. One is helium, and then one of them contains hydrogen. So complete each of the following statements that I'm going to be listing with either are they different or are they the same? So, is the pressure inside of the two balloons different or the same? Assuming, again, they're the same size, they're in the same conditions, the pressure is going to be the same. Something else. What about the temperature? Again, kinetic molecular theory says that, it's going to be based on or proportional to the Kelvin temperature here. They are going to be, you guessed it, the same. What about the number of moles in both? Again, the volume of the balloon is the same. That means that the number of moles is the same. What about the densities of the gas? Now, notice, right, that none of the stuff that we've talked about with regards to Boyle's law, Charles' law, all that stuff, had anything to really do with density. We were able to derive density, but technically the density of the gas is going to be different. Helium's density is going to be different than hydrogen's density. Okay, but realize that kinetic molecular theory allows us to make all of these suppositions and all of these ideas that we've been basically toying around with for the last couple of videos. It's all because of kinetic molecular theory. Okay, again, so here's kind of like, again, a good application of that. Let's sketch a graph of pressure versus volume at constant temperature and constant moles. This is kind of what we would get. So we get this nice curved graph. Pressure is on the y, and then I've got volume on the x. Okay. Notice we get an inverse relationship here. So as the pressure is high, the volume is low. As the volume is high, the pressure is low. What about volume versus temperature at constant pressure in moles? And technically, this temperature is at degrees Celsius. See if you can think of what that would look like graph-wise. This is one of the cool things you could do. So most of the time, we would see the graph, and it would just be this half of the graph, okay? But, and so by the way, this is based on experimental data that someone collected here, okay? So these 2 points that are on the positive end here, eventually you hit, the 0 degrees Celsius. But here's the beauty of, degrees Celsius. If we continue the graph beyond that, eventually, since this is volume on the y and this is temperature on the x, eventually, if we continue the line, it will eventually cross the x at a 0 point. And that would technically be when the temperature is, you guessed it, as low as it can possibly be. This is one of the ways you derive absolute zero. And this is one of the easiest ways of deriving absolute zero. Now here it's, negative 289 degrees Celsius. It's not exactly, the negative 273, but that's because this is just an experiment that someone conducted, and I thought it was an interesting graph. So pretty cool, though, that you can just extend this down and then inevitably find a point that is between negative 300 and negative 200 degrees Celsius, and that would be the theoretical, 0 point, let's say, for temperature. Now, let's say that instead I'm doing volume versus temperature in Kelvin. So again, we can assume, okay, now we get a nice graph that's going to go towards 0. And notice, just like the last graph, it's a nice straight line. It is a direct relationship between volume and the temperature in Kelvin. And one of the beauties is, again, we now have a 0 point where it's 0 volume and it's 0 temperature. Good old absolute zero. What about moles versus volume at a constant temperature and a constant pressure? Again, a graph of volume versus moles, you can see it's a nice straight line. And that straight line is going through when the volume is 0, the number of moles is 0. It would continue if we kept going. All right. So now let's kind of take a look at something that we looked at last time, which was this PhET interactive simulation. And I wanted to kind of show you the why of this. So we haven't really looked at the reason why these things are true, like Boyle's law and Charles' law. So let's kind of explore the reason why these things are the way they are. So these particles that we're adding are just going to be regular old particles. Notice that the more gas I add, the higher the pressure is. And again, that makes sense because remember, according to kinetic molecular theory, it's the collisions between these molecules that are causing the pressure. So now let's adjust the volume. So again, if everything else is kept constant, what do we assume is going to happen when we change the volume of the container by making it smaller? I'll cut it by half. Notice that the pressure increases. Now think about why that might happen. This happens because now, since we have less volume in here, so if we're looking at the inside, the surface area, right, that means that we're going to have more frequent collisions between the little molecules here are atoms, and the container. That should make the pressure go up, and it does. Now, what happens if I shrink it? Again, if I shrink it, you would imagine that now collisions become less frequent, and so pressure goes down. Let's increase the temperature. Look at what happens to the pressure. Why would that increase the pressure? I'm adding more kinetic energy. The average kinetic energy of this has increased, so there are going to be more collisions because these molecules or particles are moving faster. They have a higher average kinetic energy. What if I decrease the temperature and absorb that heat? You guessed it, now we've got low pressure. I don't actually know how low the simulation will go, but you get the idea. Look how slow these molecules are moving now. And so again, much like we've talked about before, this is just one of the many ways that we are able to kind of use what we've done already to predict kind of what is happening in these types of situations. So here's another little concept check. I have a sample of nitrogen gas in a container that is fitted with a piston that maintains a pressure of 6 atmospheres exactly. So I'm keeping a constant pressure of 6. Initially, the gas is at 45 degrees Celsius in a volume of 6 liters. Then I decide to cool the sample. Which best describes the final result that occurs once the gas has been cooled off? So again, think about this, right? I've got this sample of nitrogen gas that's in here. Pressure has to be constant at 6 atmospheres. That's not allowed to change. So this piston is free moving. It can move up or down. Initially, the gas is at 45 degrees and the volume is 6. What do we think is going to happen when it cools off? Does the pressure of the gas increase? The volume of the gas increase? The pressure goes down, the volume goes down. Both pressure and volume change. What do you think? Answer: the volume of the gas decreases. Now you might think, wait a second, shouldn't the pressure and other stuff also change? No. So if the piston is maintaining a pressure of 6 atmospheres, that means it can freely move up and down. The volume of the gas is going to be the only thing that's going to change with the temperature. This is virtually Charles' law because the pressure is constant. All right, now again, here is our little hint that I put here as like a little backup. You have a movable piston in this situation, but let's actually, solve some stuff and prove it to ourselves. So I have 6 liters. Again, 45 degrees Celsius is great and all, but I need to convert that to Kelvin, so I have to add 273. And then my new temperature is 15 degrees Celsius, so I have to add again 273 to make that consistent. And then I have my, volume over here. So all I do is I solve for volume and I get 5.43 liters. So it goes from 6 to 5.43. Does that make sense logically? It should make sense, right? If I'm lowering the temperature, then the volume should decrease and go down. And again, most people say, oh, wouldn't the pressure go down? The pressure is able, again, the piston means that it is able to move up and down freely. So the pressure here is going to be something that is constant in that situation, so it wouldn't be changing. Now, here's another little kinetic molecular theory little part. And so we didn't really talk about, postulate 4, about the average kinetic energy being equal approximately to the Kelvin temperature of the gas. So root mean square velocity, this is a formula that's super weird, but very useful to us. So here's what these stand for in case you're wondering. So this is the root mean square velocity. That's what this little symbol here is talking about. R is going to be a constant, but here's the thing, universal gas constant, right? We've talked about that. We called it R before. That is, liters times atmospheres per mole degree Kelvin. R also could be expressed as a constant where we're looking at joules, which is a unit of energy, divided by Kelvin moles. So this is just a different format for our usual R value. This is just, joules instead of liters and atmospheres. Now we're looking at joules. So Yes, it's the exact same constant. It's just that, when you change your units, obviously the number is going to shift and change. So R in this situation is still a constant. T is the temperature of the gas in Kelvin. M is the mass of a mole of that gas in kilograms. That's unusual because normally when we do molar mass, right, it's looking at grams, but in this case, it's going to be in kilograms. Now, when you use this kind of formula, the final units are going to be in meters per second. How fast is your gas moving in meters per second? Now, the reason why we use this, RMS, so we're using the root mean squared velocity instead of the average, right? Just straight old average, is because typically in a gas sample, the net velocity is going to be zero, right? The particles are moving in all directions. And so since it's moving in all directions, the average velocity is actually going to be basically zero. It's going to be as if the gas isn't moving, which is dumb, right? Because in the last simulation I just showed you, clearly the gas was moving around. So if you want to get into the nitty gritty of it, it's because of a physics thing. That's the reason why the net velocity would be zero. So instead, we like to do the root mean squared, where now we're looking at like the actual movement of how fast the gas is moving instead of just saying, oh, well, of course, it's moving in all directions, so the net velocity would be zero of the gas molecules, even though we can clearly see them in motion. Okay, so that's just an interesting little application of that last part of kinetic molecular theory. Now, how are we going to use this information? Well, normally the way that we use this type of information is in the last part of this gas law stuff, which is about effusion and diffusion. So diffusion, by the way, is just a term for mixing gases. And if you're thinking, wait, can it apply to liquids? Okay, technically it's the mixing of fluids, but we're studying gases, so we're just saying it's the mixing of gases. Effusion describes the passage of a gas through a tiny hole into an evacuated chamber, which just means a vacuum. And then the rate of effusion is a measurement of the speed at which a gas is transferred from, this little hole basically all the way through to the vacuum. So effusion versus diffusion. So diffusion is, in this case, let's look at this. We got our little blue circles here. Let's say those are air molecules, and I have a nice little bottle of, let's say, perfume that I'm opening up, and the perfume is going to be represented by these little green ones, these little green circles. And so this is diffusion because notice that randomly the molecules are now spread out. Effusion is I have a sealed container of gas, or in this case, multiple gases, and I'm going to open it up. So I'm opening up a tiny little hole, and now the gases are escaping. That's effusion. So diffusion, effusion, a mixing of gases. In this case, notice also that at the beginning of this, it's all evacuated. There's nothing out here. It's all in a vacuum. And now I'm letting the gas out through this tiny little opening or this tiny little hole. So again, that's kind of what effusion is. It's basically you have your container of gas, there's a little opening, and you're letting the gas molecules go out like one at a time into this vacuum. We can measure the speed at which they're moving, and that would be the speed of effusion. So let's talk about Graham's law. Graham's law of effusion is an interesting law. It's that the rate of effusion, so how fast a gas moves, is in some way proportional to this. So if we are comparing two gases and how fast they are escaping, the rate of effusion of gas 1 divided by the rate of effusion of gas 2 is equal to the square root of the molar mass of gas 2 divided by the molar mass, or square root of the molar mass of gas 1. So like it says, M1 and M2 represent the molar masses of your gases. So now let's use Graham's law of effusion in order to solve this type of problem. So what is the molar mass of a compound that takes 2.65 times as long to effuse through a porous plug as it did for the same amount of, in this case now we have xenon difluoride, at the same temperature and pressure? So let's calculate this stuff, right? So here's kind of how that works. I have the rate of effusion for gas 1 divided by the rate of effusion for gas 2, and that's going to be equal to the square root of, in this case, M is the molar mass. So the molar mass of our number 2 gas divided by the square root of the molar mass of our number 1 gas. So looking through this problem, it looks like we have everything we need. Maybe you might think maybe it doesn't look like we have everything we need, but we're going to make some assumptions. So the first thing is it doesn't matter whether you pick xenon difluoride to be your first gas on this, or if you choose the unknown gas that we're trying to calculate to be your number 1 gas. It doesn't matter, but I'm going to choose the rate of effusion for gas 1 to be equal to 1, and I'm going to say that the rate of effusion for gas 2 is going to be equal to the 2.65 here. Now you might think in your head, okay, but like, did it have to be 2.65? Technically, I could have picked any number here and then just said the rate of effusion for gas 2 was 2.65 times that number. But again, to make things easy, why not just make this equal to 1, and then I can just make this 2.65. So now I've got my molar mass of number 2 here. That's going to be 169 grams per mole. That's the molar mass of xenon difluoride. And then I've got my molar mass of, number 1, which is my unknown, my x. So here's how I would set that up, right? I have my 1 over 2.65. I have my square root of 169 over a square root of x. And so what do I get? Well, when I do 2.65 times the square root of 169, I get 34.45. And then, of course, I'm going to need to, when I multiply these, I just get the square root of x. So to get x by itself, I will square this. To get x, I will square this. And now I end up with about 1,190 grams per mole. So and I guess that makes sense, right? If this is going to be moving 2.65 times slower, whatever it is, through this plug, that it's going to have to be a lot heavier. And in this case, it's significantly heavier. Now, what about real gases, right? So here's the thing about kinetic molecular theory. It's really an ideal gas that we're looking at in all of these situations. And so an ideal gas is a hypothetical concept, right? No real gases follow the ideal gas law exactly. No real gases that you're going to come across perfectly follow every single one of the gas laws that we talked about. And so the reason why we like using them and approximating them using all of these different gas laws that we've talked about is that at low pressures and high temperatures, most real gases behave like ideal gases. So for example, if I have a sample of CO2 at low pressure but high temperature, you might think, what's low pressure? What's high temperature? Aren't those kind of like, vague terms? They are vague terms because for certain gases, it depends, when we say at a high temperature and a low pressure, it might be something completely different for a different gas. But in theory, most of the gases that we come across every day are at low enough pressures and high enough temperatures that they behave like ideal gases. So it's perfectly acceptable to be able to approximate their movements using that. So when do we have to correct our equations? Well, the only times we really need to correct these equations are when the pressure of the gas is really high, when we have a high pressure inside of like a tank or something, or as we get closer and closer and closer to absolute zero, which again, for everyday experiments, we're not going to be under these conditions. Now, why do we have to correct under these conditions? Well, the reason why is that if the pressure is high enough, the concentration of gas is going to be really, really big. And if the concentration of gas is really, really big, then the fact that these gases are attracted to one another or repelling one another becomes super, super important. Remember, in the kinetic molecular theory postulates, we assumed that there was no attractive force between the particles. They were just bouncing off of each other. Well, I hate to tell you this, but if you get something that has such a high concentration of gas in it, then they're going to be basically attracted to one another no matter what. So here's kind of how that breaks down. So notice, right, that at high temperatures, so 673 K, there's not a lot of deviation. This is how it should react in an ideal gas, and this is pressure. Notice that, even from here to about 200, atmospheres, which is ridiculously high pressure, pretty good. Like they're behaving similar enough that you wouldn't really think there's that big of a deal. Now, the only one that's not really behaving like that, so the 673K and the 293K are kind of okay in that range. The only one that isn't is the one that's 203 Kelvin. So notice that you can imagine, right, with nitrogen gas, that if I got even colder, this curve would be even more ridiculous because of the attractive forces. So this is kind of the reason why, like, and picture this, right? Under most of our time, we're like, what, at 1 atmosphere, which is like so close to the 0 mark here. And normally we're at, 200, let's say, and 90 something K. Well, again, we're really close to being ideal already in those conditions, which is why we like using the ideal gas law. But if you're getting super cold, or if the pressure is ridiculously high, notice there are some pretty significant deviations. So what do we use in that situation? Well, we still use PV equals nRT. The only problem is we have to correct it. So real gases use the van der Waals equation. And so the van der Waals equation is this kind of part here. So we have to basically correct for pressure, and we have to correct for volume. And so notice that N is just like we've been using. It's the number of moles. V is volume, as you already know. But A and B, what the heck are A and B? So A and B, these are going to be constants that you can look up for any gas. There's a nice table of them. So P here is now corrected pressure. And then V, this is, corrected basically volume. But normally A and B are so negligible when we're dealing with, things at our temperature and our normal pressures that they basically become 0. So it would be like whatever pressure we observe plus 0 times the volume minus 0. And so under ideal conditions, these things just drop away and we don't even need to worry about them. But if we're in, like we did on this side, so I'll go back, under some pretty crazy conditions with high pressure and low temperature, then we're going to have to correct our pressure and correct our volume. So here's kind of, again, when we're looking at attractive forces, the kind of attractive forces we're talking about. But because, the pressure and volume are going to be different, we have to correct for them. So A, though, that little A, reflects how much of a correction must be made in order to make sure that our pressure is going to match our ideal, kind of gas equation. And so if we have a low value for A, that means that we have a very weak intermolecular force among the gas molecules. But again, for helium, you can just look it up. If you have helium, or you have, carbon dioxide, or you have methane, or you have water, generally speaking, the lower A is, the less attractive the force is between the molecules. And you can notice that helium, neon, argon, krypton, they're all noble gases. So they're not going to have a whole lot of that kind of interaction. But as we go up here, you can see that water has a pretty high attractive force. In fact, it has like the second or third highest attractive force. And that makes sense because it undergoes hydrogen bonding, which is a pretty strong kind of force. Now, section 5.9 is about characteristics of real gases, and so we're going to go through this kind of quick. So with air pollution, there are two major sources: transportation and producing electricity. So when we combust petroleum, we get carbon monoxide, carbon dioxide, we get nitrogen monoxide and nitrogen dioxide, along with a lot of other unburned molecules from petroleum. So nitrogen oxides, due to cars and trucks, at high temperatures, nitrogen gas and oxygen gas will react to form nitrogen monoxide, which will oxidize to form nitrogen dioxide. And so nitrogen monoxide and nitrogen dioxide are not good for you. You wouldn't want to breathe them in. They're high pollutants. And so, like it says, nitrogen dioxide breaks up into nitric oxide and free oxygen atoms. And so we call those free radicals. But in reality, what the interesting part of this free radical of oxygen is, it can combine with oxygen in the air in order to form ozone, O3. And so here's kind of that process. So I've got, again, my nitrogen dioxide, I've got radiant energy from, let's say the sun, and that's going to make my nitrogen monoxide, and I have a leftover oxygen. Notice that's not O2. This is a free radical of oxygen. It's got a lone electron that is going to be super reactive. So if you ever heard in commercials people talking about, antioxidants, antioxidants remove these free radicals of oxygen. So now I have my free radical of oxygen in my oxygen gas, and now I've manufactured ozone, an allotrope of oxygen, which is in our atmosphere. So depending on the time of day, this is kind of interesting. Some smog peaks at different times of the day. So obviously you can see that, like, at night, there's not as much petroleum molecules because there aren't a lot of people driving, but it starts to get really, really bad as people go to work. So right at like 8 o'clock. Notice though that some of these other pollutants peak at different times. So, nitrogen oxide, nitrogen dioxide, they peak in the morning also. The weird one is ozone peaks at noon, and you might think, why? So sunlight helps to catalyze a lot of the manufacturing of ozone. And so since it's, catalyzing it, you get a lot of it happening when it is the sunniest, believe it or not. And so that's right around noon normally. So sulfur oxides, those are due to burning coal for electricity. And so sulfur produces sulfur dioxide when it's burned. Sulfur dioxide oxidizes to sulfur trioxide, which can combine with water droplets, making sulfuric acid, which is H2SO4, by the way. And so here's that process. We've got sulfur, which is in minor bits of coal. We've got our oxygen gas. We're making sulfur dioxide. 2 sulfur dioxides and an oxygen molecule will make 2 sulfur trioxides. And now we've got sulfur trioxide and a water molecule generating sulfuric acid. So again, that's acid rain. Now, the weird thing about sulfuric acid, other than the fact that it's corrosive and produces acid rain, is that it can be very easily absorbed by things, sulfuric acid. And the even crazier thing is that you can remove sulfur dioxide from these gigantic smokestacks that you sometimes see and releasing pollution or whatever maybe you think it looks like pollution. Normally now, those giant smokestacks actually are mostly, let's say, water vapor, because they use a scrubber to remove the sulfur dioxide from the gas of burning coal. And so here's kind of that process. So we've got calcium carbonate here, coal and air going in. So you can see we're still manufacturing, our sulfur dioxide here, which is not good, and we wouldn't want to have that in getting released into the atmosphere, but it's being scrubbed. And the way it's being scrubbed, which is kind of cool here, is it's being scrubbed by water and then calcium oxide. And by doing that, what you're actually manufacturing with this SO2 here is you're manufacturing calcium sulfite. And calcium sulfite will solidify and just kind of fall to the bottom of your smokestack. So the actual smoke, quote unquote, that is being released to the atmosphere has now basically removed one of the most hazardous gases by just mixing it with water and calcium oxide. It will take all of that unreacted sulfur dioxide and turn it into calcium sulfite, which is, relatively harmless and actually used in many things. All right, well, that was one of the longest videos that you could probably ever watch on here. So if you have any questions, please let me know. But like and subscribe, and we'll be going through our next chapter of Zumdahl 7th edition.